Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year, we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen.
All right. Well, hello, everyone, and welcome to this webinar. Good morning, good afternoon, or good evening, depending on where you are joining us today. Thank you so much for tuning into our webinar, Efficiency Matters, the Key to Thriving Green Hydrogen Projects. Today, I will be the moderator of this session. I'm Christina Galan from ATA Insights, and we are very lucky today because we have an excellent speaker with us, Dr. Rasool Aghatehrani, who will be talking about everything that we need to know about efficiency in green hydrogen projects. Before we start, I do have a couple of housekeeping rules to mention, and then we will follow up with the webinar presentation. So as we said in the video before, if you're tuning in now, this session is going to be recorded, and you will have the video in the recording of the video in a couple of days. Also, if you are connecting from YouTube, you have a chat there, so please feel free to get all your questions there, and our team will send them our way. If you're connecting from Zoom, you have on the right-hand side a chat. Feel free to introduce yourselves. Let us know where you're coming from, what do you do, why you're interested in green hydrogen projects efficiency. And if you have any questions, you have a Q&A box right below that we will answer after the presentation. We will answer the questions in the order of appearance. However, please note that some of these questions will be answered offline after the webinar due to we want to focus on efficiency, and we want to give a chance to everyone to ask their questions. So without further ado, it's a great pleasure to present Dr. Rasool Aghatehrani, who is the Chief Marketing Strategy and Fleet Operations Manager at Ohmium, the equipment manufacturer for green hydrogen solutions. So I want to say a big welcome to Rasool today for joining, and thank you for joining us. And whenever you're ready, you can start putting up your presentation, and we are ready to go.
Thank you, Christina, to you and your team for hosting the webinar today. Good day, everyone. Thank you so much for joining the discussion today. As Christina mentioned, the discussion today will be about the efficiency and why it is so important in green hydrogen production. Can everyone see my screen? Yes, excellent.
Yes.
So for the conversation today, we briefly introduce Ohmium. Of course, this is not about advertising Ohmium, but just a quick introduction. And then we dive into why the efficiency is important in green hydrogen production, and what are the contributing factors, major contributing factors in green hydrogen production. Of course, we need to assess this from the technical perspective first, but it's always to see how these factors will affect the project's bottom line, which is like project competitiveness, profitability, and hydrogen price. Of course, you may look at it from the hydrogen price perspective or the project net present value perspective. So we will discuss both of them. And then we look at it from a more comprehensive overview of like how best we can optimize a project end to end to have the best, to leverage the efficiency and leverage the electrolyzer features to have the best and most profitable project. And as Christina mentioned, after that, we will definitely get into the Q&A. So looking forward to discussing your questions with you. With that, a quick overview about Ohmium. As Christina mentioned, we are a PEM electrolyzer manufacturer. Our electrolyzer is very modular, like Lego pieces, that provides three major, advantages for your projects. Number one is the most or one of the most efficient electrolyzers in the market based on the publicly available information. Of course, we will discuss the importance of efficiency. Number two, our electrolyzer is built to be easily installed and rapidly installed, and that significantly reduces the installation and engineering and construction cost for the project. And the third item I want to briefly talk about is the footprint. Land is important, and it also affects all of the auxiliary connections between the electrolyzers. So we have one of the highest footprint density in the market at around 29 square meter per megawatt. The company is headquartered in the US in Silicon Valley. I'm in San Francisco Bay, and we do the manufacturing in India so that we provide the best of the two worlds, the best IP, intellectual property rights, matched and paired with the attractive cost of manufacturing in India. If you are interested, please reach out, and we would be more than happy to discuss the solution, the hydrogen solution we provide in more details. Now, about the system efficiency. So when we look at the green hydrogen production, of course, the industry focuses on the heart of the electrolyzer, which is called the stack. And you can see the stack noted here as the, one of the main contributing factors to the losses. However, there are other items because generally we start from the AC power generated by renewable electricity or coming through the grid from, wind farms or hydro turbines or nuclear power plants. And then we would like to, in most applications, to get to some sort of pressurized hydrogen at a specific purity. As an example, if you look at ammonia plants, they generally use hydrogen at 30 to 40 bars. There are different other different pressures too, but that's kind of like very norm. And at the purity of 4 to 5 nines, 99.999% purity. When we look at that, it's very important for efficiency and energy consumption to capture all the contributing factors to the energy consumption. And this is very important because if you look at the hydrogen price, about 60 to 70% of the hydrogen price is the cost of electricity. So we need to capture every item. Here I try to create these, you may call it loss tree, to show what are the important factors we would like to consider in this estimation. If I start with the AC power coming from the grid, generally we will have auxiliary loads at the project such as water treatment system, cooling system, data acquisition system, controls, and telecom. Then, as you know, the electrolyzer stack uses the DC power. So we have power rectification or power electronics that are converting the AC power from the renewable electricity or the grid to DC power that can be used by the electrolyzer stack. So there are some losses there. Generally, the losses are between 2 to 4% of the electricity. Then we have the stack, and that is main contributing factor to the efficiency. After the stack, we have hydrogen here. Basically, the electricity is converted to hydrogen at the stack level. And generally, in PEM electrolyzers, the hydrogen is very pure. However, it has some level of water contents or vapor contents. In the alkaline solutions, in addition to water, there are many other impurities that is needed to be purified. So based on the technology, there will be dryers or there will be purifiers and dryers here. And generally, they also have some losses. If you look at the different technologies as an example, the pressure swing absorption drying technology or PSA may have 5 to 15% of the losses. And then thermal swing absorption technology may have a little bit less losses, but there might be some safety concerns around that. And then as we briefly discussed, the hydrogen needs to be pressurized, so there could be additional losses for the compression. Some of the electrolyzers provide the hydrogen at the pressure. Most PEM electrolyzers in the market generate a pressure through electrochemical compression. We will briefly discuss that. Some of the alkaline solutions in the market are pressurized alkaline, and basically, the water is under pressure, so everything is pressurized. They also generate hydrogen at the pressure. But if the pressure is lower or the electrolyzer is called atmospheric pressure electrolyzers, they don't generate pressure. There will be compressors, mechanical compressors outside of the electrolyzer to generate the pressure required. So end to end, we need to calculate all of these loss factors in our efficiency calculation. Now, if I kind of like as a generic item, if I calculate those items, you more or less see something along the bar graph shown here. If I use the hydrogen higher heating value at around 39.4 kilowatt hour per kg, we will add all of these losses to get to something from 48 to 60 kilowatt hour per kilogram as the system efficiency. Although we call it efficiency, you can calculate the efficiency as a percentage, but in our industry, generally, we are very interested to see how many kilowatt hours is used for every kilogram of hydrogen, and you may call it a specific power. So the higher efficiency means the smaller specific power or less number of kilowatt hours for every kilogram of generation. In this example, 48 would be much better than 60. If I just use some of the electrolyzer, the information from the electrolyzers publicly available, we may create a bar graph as it's shown here. Of course, I try to stay, fair. Of course, I'm biased toward Ohmium, but try to stay very fair. The numbers you more or less see here is at the system level for a one-to-one or apples-to-apples comparison. As an example, if you see another solution with a stack efficiency of like 48 or 49, when we add the rest of the items to make it apples-to-apples comparison, we may end up with 56 or 57. So this is the kind of like the numbers at the system level. And as you can see, PEM and alkaline are more or less distributed in this bar graph. The lower alkaline, the more efficient alkaline solutions are more or less the pressurized alkaline solutions. They are one of the solutions in the market, mostly out of China. There are, pressurized alkaline solutions also headquartered in EU, but most of the pressurized alkalines that we have seen in the market are from China. And then the less efficient alkaline solutions are mostly atmospheric alkaline because electrochemical they don't have electrochemical compression or any compression. Therefore, compressor inefficiencies would be added there. Generally, some people believe they are safer. than the pressurized alkaline. On the other hand, you see PEMs. PEMs have a very different structure. They have a solid barrier between the oxygen and hydrogen side. And as a result, pressurized PEM would be very safe. The PEMs you see here are more or less pressurized PEM. I have provided some information here in a footnote about what is the specification for the apples to apples comparison. I try to convert the efficiency to the system level, estimating all of these losses based on the publicly available information to get to 99.999% pure hydrogen at 14 bars. And then, of course, we more or less model the electrolyzers at 50% capacity factor. It doesn't affect the efficiency here, but you will see it in the techno-commercial comparison. And then one last thing, there are conversations about alkaline Faradic inefficiencies that could be up to 10%. BNEF had a new article about that a few months ago. If you are more interested, that is not modeled here, but potentially that can further decreases the efficiency for the alkaline solution. With that, now maybe we get into looking at some euro numbers and dollar numbers. At the end of the day, that is the most important factor for a project to be competitive or not. In this process, generally the way we work and we create a partnership with project owners and project developers is more or less to work with them to provide the most optimal solution. But when you want to optimize a solution, the freedom of angles we have here is very important. If we only look at the electrolyzer, of course, there are potentials for opportunity, but more or less the best metric for that is price tag of the electrolyzer. So it becomes a haggling of like the electrolyzer price. But when we expand our scope a little bit, the scope of optimization, and look at the hydrogen project, then there are more opportunities for optimization. As an example, how the electrolyzer pressure will affect the compressors required. How about how the power electronics or rectifier in the electrolyzer will affect the harmonic filters required for the project or not. And therefore, there are more freedom in optimizing the project. There is more room, and as a result, the results could be better. In general, to make sure that any technical optimization will be assessed commercially, most people use the levelized cost of hydrogen as a best metric. We will discuss about LCOH. Some people may prefer to just look at the net present value or profitability of the project or IRR instead of LCOH. So basically, it's either LCOH at a specific IRR or IRR at a constant, hydrogen price. But we also would like to request our, project owners and clients to even go beyond that. Sometimes, of course, the hydrogen is the end product, but in many cases, we have seen the end product is something else, like green steel, green ammonia, or, sustainable fuel. And that's where we even see more opportunities for optimization. As an example, if we expand the scope of optimization in collaboration with the project owner from the hydrogen project to looking at the interaction between hydrogen project and, as an example, the ammonia plant, or hydrogen project and renewable energy resources, or hydrogen projects and the power grid, we see even further optimization opportunities. To just give you an example, what if the solar and solar photovoltaic plant and the hydrogen project are co-located, and we can connect directly to the solar on the DC side? That means we don't need solar inverters, we don't need medium voltage transformers. On the solar side, we don't need medium voltage transformers on the hydrogen side, and we don't need rectification on the hydrogen side. If you look at that as a rule of thumb, that will remove about 7 to 9% of the capex, and it increases the efficiency by about 7 to 9%. Or if you look at the power grid, what if the electrolyzers can participate in the frequency regulation market? I believe we all saw the blackout last year or earlier this year in Spain. So supporting grid from the projects, from the hydrogen project could be very valuable and create another revenue stream for the project. And at the same time, when we look at the ammonia plant or a steel plant, what level of purification is required? So all of these will help us to further optimize the project as a solution and make the project more profitable. In those cases, instead of levelized cost of hydrogen, we more or less work with our clients and our project owners and developers on the levelized cost of steel or levelized cost of ammonia, LCOA or LCOS. So X here could be the end product that is the green solution end product for the project. With that, now what is LCOH? Basically, LCOH is the levelized cost of hydrogen, and this is the metric to measure the average cost of hydrogen over the project life. As you all know, there is a value to the time of the money spending, and there's a value to the time of the hydrogen production. As an example, if someone asks you, would you like to have 1,000 euros now or 1,000 euros in 10 years? Of course, you may say now because there's a value in the time. So to calculate the levelized cost of hydrogen, we need to estimate and include the value of time in all of the calculation. That's where you see the LCOH equals to the present value of all of the operation costs, present value of plus the present value of all of the capital spending, divided by the present value of all the hydrogen produced during the lifetime of the project. In this graph, I try to show that all of the operation cost in gold and yellow, all of the capital spending in blue, and the hydrogen production in green. It's very obvious that the higher hydrogen production will decrease the LCOH, and any less spending on the OPEX side or the CAPEX side will increases the LCOH. The size of the blocks here is a very, very estimated size of, what percentage of the LCOH would be contributing by every one of these items. But of course, we can look at it at the details and calculate each item in this workshop today on the efficiency side. Now let's get to the numbers. We briefly talked about this graph when we mentioned about the apples to apples comparison between the efficiency of different electrolyzers. For this exercise, I just tried to compare the value of efficiency for our solution at 48 with the value of efficiency of this electrolyzer, which is a pressurized alkaline at 52.4 kilowatt hour per kg. You see some of the assumptions. This is with the very generic assumption with a WACC of weighted average capital cost of about 9%, project IRR of about 10%, and more or less 50% capacity factor for the project at the energy price of about 34 euros. If you look at that, efficiency helps the project in two fronts. The first side is that higher efficiency means for every kilogram of hydrogen, the project will use less electricity. In this case, this project is using around 4 kilowatt hour less electricity for every kilogram of hydrogen. And that means, there's around 15 cents of saving because the project has used less electricity. But at the same time, if the project needs to generate For simple example, 1,000 kilogram of hydrogen per hour. With this electrolyzer, more or less, you may need 48 kilowatt hours multiplied by 1,000. In other words, 48 megawatts. But for the other alkaline, the project will need at least 52 megawatts. Therefore, for meeting the demand of the hydrogen, the higher efficiency means the project will be also smaller from the kW capacity perspective. And if you look at the market right now, the electrolyzers are priced as euro per kW. Therefore, there's another angle of saving, which is created by having a smaller megawatt capacity for the project to meet the hydrogen demand. And when you add these two, instead of only the saving on the electricity side, there will be saving on the electricity side plus the saving on the size of the project. Of course, the number you may see here would not only affect the electrolyzer size, but also will affect the medium voltage transformer, high voltage substation side, and everything that's contributing to the project, including the installation cost. So interestingly, the value of efficiency is beyond only using less electricity. It's more of also having a smaller project to meet the same hydrogen demand. In this case, the around 4 kilowatt hour per kg better efficiency will decrease the levelized cost of hydrogen or hydrogen price by about 27 cents. Now, some people would prefer to look at the net present value of the project. In other words, how much of equivalent CapEx saving this better efficiency will create. So we can look at it from the net present value perspective. The value of efficiency is about 135 euros per kW, and the value of a smaller project capacity is about 104 euros per kW. So the total value created by the better efficiency in terms of saving equivalent CapEx is about 239 euros. In this graph, I just try to provide you the both perspectives. You may select whichever you like the best, but more or less from the financial perspective, they are the same numbers. Now, another factor we discussed about is the compression. In the previous efficiency estimation that we just discussed here, we compare, as an example, Ohmium as an example solution with a pressurized alkaline. But what if we compare Ohmium with another one of these electrolyzers, which is not pressurized, it's just atmospheric? So the other factor we need to consider is about, in efficiency calculation, is about the compression. In other words, if the electrolyzer is not generating hydrogen at the pressure, there needs to be hydrogen compressors to pressurize the hydrogen so that we can get to apples comparison between the solutions you would like to use for your project. My background is electrical engineering, but I have had the pleasure of working with process and mechanical engineers. And one of the things that I have learned over the last 5 years is pressurizing gases in low pressure is very inefficient, but pressurizing gases in higher pressure becomes very efficient. One of the main reasons is that at the low pressure, each stage of the mechanical compressors only can increase the pressure by 3 to 4 times. As an example, if there's an alkaline solution or PEM solution that generates the hydrogen at the atmospheric pressure of, like, let's say 0.2 bar, there's a need to get to there's a need for one stage of the compressor to get to 1 bar, another one to get to 4 bars, another one to get to 14 bars. From here, you see it's much easier, because from 14 to 60, it can be 1 more, and 60 to 180 or 200 could be 1 more. So mechanical compressors at a higher pressure could be easy and efficient, but at the lower pressure, they are not very efficient. And that creates a problem because compressors are expensive, and now we need 2 to 3 stages of the compression. They are mechanically rotating machines, so they are expensive to maintain. There's an overhaul for the compressors, and also they are inefficient, so they use electricity. In this case, for hydrogen to go from 0.2 bar to 14 bar, in an ideal situation, there need to be about a little bit more than 1 kilowatt hour per kg of electricity, but none of the compressors in the market is 100% efficient. And actually, at lower pressures, they are very inefficient. Therefore, it would be a little bit more than 2 kilowatt hour per kg. So this will affect the project from the compressor capex and installation, the compressor maintenance cost, and the additional energy used by the compressor. So when you look at that, that's another 30 cents of cost. Now, if you look at some of the pressurized solutions such as Ohmium PEM, where the solution, the PEM, can generate hydrogen at the pressure safely, everything is done electrochemically. So there's no mechanical compressor inside our solution, and it generates the hydrogen at 14 bars. So the project will save all the stages of compressors noted here. And this system is very efficient from the electrochemical compression perspective. So you don't see the energy consumption here. It's already included in the electrolyzer efficiencies or stack efficiency. And then there's no OPEX for the compressor anymore here. That's more or less the OPEX of the electrolyzer. So that's around 30 cents of saving on the hydrogen price, or 242 euros of saving, equivalent saving on the CapEx basis. Now to conclude, if I add just these two together to compare one electrolyzer, in this case Ohmium, from the efficiency perspective with, let's say, atmospheric solution in the market, you will see the value of the efficiency is here, and the value of electrochemical compression that we discussed is here. So the total value is about 57 cents or 511 euros CapEx equivalent euro per kW. So this can significantly affect the project bottom line, and better efficiency with an electrolyzer that generates the hydrogen at the pressure can significantly increase the value of the project. With that, maybe I just circle back. We talked about Ohmium solution, our solution, which is extremely modular. All of these cabinets you see in this picture are fully assembled and tested at the factory for ease of installation at the project site. And it's a comprehensive solution to go from the AC power, as you can see here, all the way to pressurized hydrogen at the high purity. So we provide the full solution to you so that you get the best efficiency along with the rapid and inexpensive installation. With that, Christina, I will return it to you for any question.
Okay, Rasool, well, thank you so much. We are ready for the questions. I see only 2 posted, so love to encourage people to post their questions. As we said, we will go in order. If there are questions that are not in the scope of this event, or that might be not focused on efficiency, as this is the topic of the webinar, Ohmium will answer it offline just for the sake, and we want to give an opportunity to everyone to join the discussion, we would say. So first question from Miguel Medina. Well, he says, ignore if questions beyond scope of this event. Can you comment on whether measures adopted by the new administration can slow down further efficiency gains that can help to close the gap with other hydrogen sources?
Yeah, that's a great question. Of course, the very good incentives that used to be in the US are not here anymore. But fortunately, the incentives in Europe and in India and in many other locations, including Japan, are strong. So just maybe I make a comment about our company. Of course, it would be very good to have incentives in the US too, but Ohmium is a diverse company in terms of global presence. And although we may not be extremely active in the US anymore due to lack of incentives for the projects, but we haven't slowed down our R&D roadmap in terms of efficiency enhancements. Would be more than happy to discuss that offline with you so that we can get to the rest of the questions.
Perfect. Well, thank you. Next question. How does the efficiency change over the life of the electrolyzer? What is the stack lifetime?
Yeah, that's a great question, Brian. Generally, as the electrolyzer stack operates, two things would happen. The efficiency of the stack will be less. In other words, the losses will increase. And at some points, it may start also affecting the capacity of the stack. In our levelized cost of hydrogen calculations, what we do is we simulate on the technical side every hour of operation of the project over the lifetime. And then once every hour will create a little bit of degradation in the efficiency. Therefore, the calculation will be accurate, and then convert those numbers to financial numbers. What is the stack lifetime is a very good question. It's very dependent to items such as capacity factor, the number of turns on and off of the electrolyzer. In some of the electrolyzers, the on-off cycle may have significantly more effect on the electrolyzer. In the PEM electrolyzer, generally, PEM is designed to be very dynamic, turn on and off very easily. So the effect on the degradation of the stack efficiency would be lower. But you may see a stack life from 3 to 8% in 3 to 8 years in the market.
Great. Thank you. Next question. Is Ohmium looking to work on PEM fuel cells? And also, is there any scope to get involved in standardization?
Yeah, that's a great question because there's so many similarities between PEM electrolyzers and PEM fuel cells. Our approach right now is to focus on the PEM electrolyzers to provide the best solution in the market. But you may have seen in the news, we have a partnership with Toyota also to work on microgrid and collaborate with them on the fuel cell side. That being said, for now, our focus is mostly on the electrolyzers. Since this is not about efficiency, would be more than happy to further discuss it offline.
Perfect. Just as a reminder, we will send all these questions to Rasool and Rasool's team. So any questions that we will mark as offline will be answered the following days, just so you know. Great. Well, next question. How much do you expect efficiency to continue to improve over the next 5 to 10 years with further technology development?
Yeah, that's an excellent question. I believe, you will see a jump in the efficiency improvement, and then everything becomes very difficult because if we go back to the graph we discussed here, for the efficiency, like in the ideal case, the efficiency is about 40 kilowatt hour per kg. So it is more or less to optimize all of the numbers you may see here between the system efficiency and this ideal efficiency number, which is the higher heating value of the electrolyzer. If I just talk about Ohmium, if you look at the first version of the product we had, the efficiency of that was at around 55 to 56 kilowatt hour per kg. And over the course of the last 3 years, we could enhance that efficiency to be 48. And that is due to, of course, efficiency improvements in all of the elements you see here. And also we have some IPs about, recovering any potential purged hydrogen that also helped us a lot. So from 48, lower than 48, it would be a little bit more difficult. Of course, if the efficiency is even more important for a specific project, the project owner may decide to run the electrolyzer at a lower capacity. As an example, if you run a 10 megawatt electrolyzer at 8 megawatts or 80% capacity, the efficiency would be better. In our technology roadmap, the next generation of the product will have the efficiency at 47 by the end of 2027.
Great. Okay, well, thank you for that, Rasool. Next question. Can you tell us a little bit about your projects in Europe?
Yes, certainly. So if you look at very good databases that is provided by Hydrogen Europe or BNEF, Bloomberg or WoodMac or even Hydrogen Council, you can see many good number of projects. The good thing is that previously we mostly saw single-digit megawatt projects, but now we see double-digit megawatts and triple-digit megawatts in different applications, from the refineries to ammonia to transportation projects. So, we'll be happy to share the link for some of the publicly available databases with you.
Great. Thank you for that. Well, this, I think, is a follow-up question from one of your previous questions. I think you did mention it. Is there also a scope for Ohmium to work on standardization of PEM electrolyzers?
Yeah, of course, we look forward to working with other people active in the industry. As an example, if we just look at the efficiency, we don't have a standard naming convention for quoting the efficiency even in our industry yet. Like some people talk about a stack efficiency, some people talk about the combination of a stack and power electronic efficiency as the efficiency of the system. And some others like us look at the end-to-end efficiency as the system efficiency. So I believe there's a need for working together to create, standardization in the industry. Some of the standard bodies are working on developing the standards, which is great. Also, there are collaboration between manufacturers and hydrogen, project owners and developers in forums such as Hydrogen Europe and Hydrogen Council. So yes, we look forward to working with them.
Great. Next question. How do you see the green hydrogen industry evolving in the next years, and what role will efficiency play?
Yes, so if you look at the hydrogen industry maybe 2 years ago, it was very hot. Everyone, left and right, made an announcement about working on hydrogen projects. And now we see only people who have real projects, and only the electrolyzer manufacturers who have real solution at a competitive price can make it happen. This is an extremely good learning for the industry to go through this cycle. And, very soon you will see others also will follow. In my past life, I worked in the wind and solar industry, and I saw exactly the same. So the industry will be robust. It's just now, compared to 2 years ago, there's not such a hype anymore, which might be not bad for the industry actually. Now, in terms of where we see the efficiency plays out, the cost of renewable electricity is high. And now we also have the huge demand created by data centers for AI. Everyone would like to get the renewable electricity for data centers. Therefore, even the electricity cost could stay as is, or could even go higher. Compared to, few years ago, of course, it's lower, but there's another huge demand created by the data centers. And that means the role of efficiency would be even more important. As the cost driver of the hydrogen, the major cost driver is the efficiency of the electrolyzer and the energy price.
Okay. Thank you, Rasool. You're on a roll today. We're being very efficient as the webinar itself. So next question. What offtake applications will develop and commercialize the fastest, such as green ammonia, green steel, e-fuels, mobility? I think this is kind of a bet guess. What's your take on this?
Yeah, that's a great question. And I think, not every market is the same. So if you look at the fundamental market drivers for green hydrogen, I generally put them in three buckets. Number one is the availability of inexpensive renewable electricity. Like if you look at Southern Europe, it's very strong on solar, and some of the locations are also very strong on wind. If you look at Northern Europe, wind is very strong. Similarly, India, Australia, Middle East, you see, solar and wind being very strong. The second fundamental, item supporting the industry is the dependency of the location to imported natural gas. When a market is dependent to imported natural gas, generally the energy price is higher, and that helps the green hydrogen to be more competitive. As an example, if you look at Europe, if you look at India, those are more or less, importer of the natural gas. And the third item is more or less, related to how close the area is to the demand. And your question is related to that. We have seen refineries moving toward having the green hydrogen. Of course, we all know about the potential demand for the green hydrogen in transportation in Europe. We see huge demand in India for the ammonia and refineries. There were many good tenders in India recently with more than 1 gigawatt of projects there. And also we see a longer term strategic ammonia plant and SAF plant in Europe and in some other geographies.
Perfect. Great. Next question came through from our team from the other side on YouTube. Why is the PV of hydrogen production is assumed in the LCOH formula? Shouldn't it be the sum of hydrogen produced?
Yes. So if you look at the equation, basically, if I go back to that slide, if you look at the equation, we are using the present value of all the OPEX. So to make sure that we have an apples to apples comparison, we also need to consider the time of hydrogen production. In other words, in LCOH, we consider the time of spending in terms of OPEX. We need to also consider the time of production in the calculation. In other words, a hydrogen produced in 20 years from now will create an income for the project 20 years from now. And every euro in 20 years, due to that income, would be less valuable than the euro right now. And that's why we need to consider the present value of the hydrogen production in addition to the present value of the operation cost and the CapEx.
Okay. Great. Well, thank you, Rasool. Next question. How do you reduce cost on the desalination plant as well as wastewater treatment plant?
Yes, that's a great question. And, there are very good water desalination technologies in the market that are based on, low heat value, low value heat. If you look at our electrolyzer, or PEM electrolyzer, or most alkaline electrolyzer, generally they operate at something like 70 to 90 degrees C. And that's not a really high value heat. It's not like few hundred degrees C, because the system would like to be very efficient, and it's more efficient it works best in this temperature range. But at the same time, it generates this heat which is like some people may call it waste heat or low value heat. But there are technologies in the market where this low value heat can be used for water desalination. If you would like to use that technology, please, reach out offline, and we can definitely work with you. What it creates is that it reduces the amount of electricity used for the water desalination.
Perfect. Well, thank you. Coming up, another question from YouTube, the participants on YouTube. Maybe we need a little bit of clarification, but maybe Rasool, you know better what they're referring to. So it said, when you showed the losses tree and the kilowatt per kilogram, you said comparing system efficiency, but what was the size in megawatts of the system you considered of this calculation exercise?
Yes, that's an excellent question. Generally, when we want to, it's not very important, but when we want to do an apples to apples comparison, the size of this is driven by the size of the project. So, as an example, in many of the cases, we use a 90 megawatt or 100 megawatt project because you can nicely fit a good number of electrolyzers from any of the electrolyzer solutions in the market in a 100 megawatt block. But the size of the electrolyzer is less important than calculating the efficiency. If the question is related to like something at the 15 kW, like really a small size electrolyzers, we generally don't look at those very small projects because like those are more or less at the lab scale rather than a commercial scale.
Perfect.
So anything between 4 megawatts, like our solution is at around 4.2 megawatts. Anything between 4.2 megawatts and gigawatts is you can use this method of calculations for.
Okay, perfect. So no clarification needed. Thank you, Rasool, for that.
Sure.
And thank you, Manuel, for the question. So next question is a bit broader, and you did slightly mention it over previously, but what is on your R&D roadmap for the next 5 years?
Yes. Thank you for asking the question. So Ohmium's roadmap is based on, number one, the product should be modular, so that it will be prefabricated and pre-tested completely at the factory, and then can be easily and rapidly installed for a very low cost of installation. We have seen that many projects in the market may have challenges with the cost of EPC. So our solution can support significantly reduce that, and that will stay in our roadmap in terms of how best we can further reduce the footprint while the system stays modular. The second item is about backward compatibility, so that the same size cabinet will be used again and again in the first generation, second generation, and now as we are getting to the third generation. So that if you decide to upgrade your system in few years, you don't have to use a 10-year-old or 5-year-old technology stack. You're like in 2032, the project can leverage the advantages in the stack technology of 2032. And the third item is related to keep improving the efficiency as much as possible. And we have gone from 56 kilowatt hour per kg to about 53.5, and now to 48. Will we go to like 42 and 45? Probably not. But as I mentioned, our plan is to go to 47 and below that in the next few years. And then last but not the least, our plan is to make sure that the technology and the materials we are using will not be a limitation factor for the technology.
Great. Thank you for that, Rasool. So next question, I'm not sure if it's a question, but maybe they want to hear your comments on this. To establish a new green hydrogen plant, it's better to break it into business units, such as solar or biomass plant, then establish water treatment plants, then establish electrolyzer plants, then storage units.
Yep.
I think this. Oh, please go on.
Certainly, that is what works well. However, as we briefly discussed in this slide, at the end of the day, no matter how you split your project, it's good to look at the whole solution holistically, because there are a lot of interaction between different pieces of the plant, and each of those interactions can create, significant advantage. I again go back to direct connection to the solar as an example. When we look at that, you remove many of the equipment between the solar project and hydrogen project, and that's a huge capex saving, about, as I mentioned, about 7 to 9%. And then every one of those equipment in between, such as the solar inverters, medium voltage transformer on solar side, medium voltage transformers on the electrolyzer side, and rectifier on the electrolyzer side, they create losses. Like each transformer loss is about a little bit less than 1%. The solar inverter loss is about 2% in average, and rectification for the electrolyzer is about 2 to 3%. So it's about, at least 7% of the, efficiency improvement, and 7 to 9% of capex improvement. So it's definitely, the project can be split into blocks, but the interaction between that blocks, would be considered in the levelized cost of hydrogen solution, or levelized cost of steel or ammonia, whichever that is, so that every one of those opportunities for optimization and value creation is leveraged.
Okay, well, thank you so much for those, your sights on the comment. So next question is the degradation with such low load factors included in your figures?
Yes, certainly. When you look at the, different technologies work differently as it is related to the degradation and load factor. So when you look at the electrolyzer from like operating at the lower load factors, some of the technologies such as PEM may not be affected. Like in our solution, you can operate the electrolyzer as low as 10% without having major issue. But in some other solutions, you may not be able to go below 40% or 50% loading. Now, in terms of the loading and the efficiency, when we look at the 100% efficiency, that was the number we assessed today. But when you go from 100% to loading to 90%, 80%, since the current density inside the electrolyzer stack goes down, the efficiency would be better and better and better. But at some point, when you decrease the loading, the constant loads, such as the auxiliary loads, such as the power consumed by the SCADA system, control system, water treatment system, they become more and more important. So if you look at the efficiency curve versus the electrolyzer loading, you see the maximum efficiency at something between 60 to 80%. At 100%, the efficiency would be slightly lower, and at like 10%, the efficiency would be slightly lower. That's why, as I mentioned in the previous questions, that you may select to run the electrolyzer at 90% capacity to get to a even better efficiency. But everything we discussed today in these studies is based on 100% capacity.
Perfect. Okay, well, to finish up, so now that we've talked about efficiency and a little bit about Ohmium, how does Ohmium differentiate itself from other major PEM electrolyzers beyond the better efficiency?
That's a great question. So number one, of course, you mentioned about the efficiency, so I would not talk about that more. Number two is about the ease of installation. If you look at some of the solutions in the market and some of the challenges that the projects are facing, it's more about receiving these large-scale parts and doing the assembly at the project site, like a chemical plant. And that is very time-consuming and very expensive to install. And then also the risk of something operating or not is high. In our solution, if I go back to the slide here, everything is in these cabinets, prefabricated, pre-tested at the factory, delivered to the project site for ease of installation. So the number two, factor is like ease of installation, no building required, everything is outdoor. The only thing required is preparation of the land. The number three is about the footprint. This solution is about 4.2 megawatts. As you can see here, it needs about 125 square meters. It's about 29 square meters per megawatt. One of the highest footprint in the industry, and this footprint is inclusive of the space required for maintenance and the access. And then the third element I mentioned is that the fourth element, third, excluding the efficiency, is that it's very comprehensive. You have everything that you need to go from AC power and city water all the way to pure hydrogen at the pressure. So we provide the telemetry, SCADA, controls, power electronics, water treatment, power distribution, and the cooling system.
Perfect. Okay, Rasool. Well, time's up. First of all, thank you so much for this great, I'm going to call it a masterclass rather than webinar, because we did go over a lot of things and you did explain beautifully. And thank you to everyone with great questions, great insights. And as we said, this recording will be sent to you in a couple of days, probably next week. If you have any questions, we're here to help. And we hope to see everyone very, very soon in another of our webinars. So thank you so much for joining. Thank you, Dr. Rasool. And we hope you all have a great day.
Thank you so much, everyone, for attending today. Christina and AT